the definite integral, and area. So far, all of the functions that we have considered when talking about the area under the curve have been positive functions, which means the rate that we were looking under were strictly positive, and the rates we calculated were also positive. So this scenario, when f of x is positive, is something that's familiar to us. So if f of x is continuous and positive, then each term that we're computing in order to get the area under the curve is represented by an area of a rectangle, where the width of each rectangle was delta x, and those are approaching 0 because the widths are getting smaller and smaller as we're putting more and more rectangles in. So when we do this, the area is naturally positive, and when we're computing the area, it's the area bounded between the curve and the horizontal axis. So for example, f of x equals x squared. This function is continuous and positive and looks like this. So if we wanted to find the area between, say, 0 and 2, we'd be looking at the area between the function and the x-axis. So each of these little rectangles would have a positive area. And so all the applications you will notice that we've done so far have had positive outcomes, which has resulted in an increase in the original function. Let's look at an example where, again, we're going to have a positive rate and a positive outcome. Example 1. The rate at which your income is changing is given by I of t equals 1.85 to the t in dollars per month, where time t is in months. Find your change in income during your first year working. So we have here a rate that describes how your income is changing. And if we want to relate that back to the original function of income, we can integrate this rate in order to find out what the change in income was. So here we're going to set up an integral, and we're going to integrate our rate of 1.85 to the t dt. And we're looking at our first year working. We need to be a little bit careful here because time is in months. So 1 year is going to be 12 months. So we need to set up our bounds from 0 to 12 because, again, we need the units of our independent variable to match the units here of our dependent variable, or the rate that we're integrating. So we're going to take this function and we're going to plug it in to determine how much our income changed, because remember, when you integrate the rate, it tells you how much the original function changed based on how the rate itself is changing. So when we plug this all into our calculator, we're going to get $2,610.86. So again, this is going to be in dollars, because if we were multiplying our rate times time for each individual little value, it would be dollars per month times month. The months would cancel and you'd be left with dollars. So your income over the first year increases by $2,610.86. I know that it increases because when I took the integral, the value was positive. Now, I want you to use your calculator, and I want you to try to compute the integral from -1 to 1 of x squared minus 1. What happens when you plug that into your calculator? When I plug this in, I get -1.333 repeating. So I'm going to round that to -1.33. So now we need to have the discussion about what this means. The fact that when we computed this integral, we got something negative. How does that fit into our picture of areas? When f of x is negative. So if the rate at which you are looking at the area underneath is continuous and negative, so now we are below the x-axis, then each term that we're computing, these little rectangles, right, the f of x value that we would use to compute it is going to be a negative value. Normally we ignore that when we talk about area, but in this context, each rectangle area is going to be counted as negative because that f of x value is negative. Therefore, the area between the function and the horizontal axis is going to be negative when f of x is negative when we are computing the integral. It's important to remember that area itself is positive by definition. When we talk about the area of a rectangle, we're talking about how much of a shape it takes up in a two-dimensional plane. So area itself is negative. However, what we're saying is in the case of an integral, we are assigning it to be negative in the circumstance of being underneath the x-axis. So what does that mean? Let's look at a picture to try to make sense of this. So here's a picture of x squared minus 1. That's the integral we just computed. I'm going to shade in the area that we were looking at. So we were considering what was happening from negative 1 to 1. We know that when we take the integral of negative 1 to 1 of x squared minus 1 dx, that equals negative 1.33 repeating. However, the actual area itself, if we were just talking about area in its mathematical definition, would be 1.33 because area talks about how much space was taken up from this shape. So the area is 1.33, but the integral is negative because the integral assigns meaning to that number, and the integral says that that meaning has context, and the context depends on whether our function was above or below the x-axis. Now I want to remind you about our relationship between the derivative and the original function. So if a derivative is negative, that means that the original function was decreasing. So here, that makes sense that if we're talking about the area of a function that's negative, it should give us a negative value because it's telling us the change in the original function, which means that if we need the original function to be decreasing, then we need that change to be negative. So let's look at some examples to try to sort out this idea of positive and negative area. Example 2. The average daily temperature from October 1st until February 1st is declining at a rate of f of t equals negative 0.98 to the t degrees Fahrenheit per day. There are roughly 92 days between October 1st and January 1st. Determine the change in temperature over this time period. So remember, what we're given is the rate at which our temperature is changing, and that is in degrees Fahrenheit per day, which means that our independent variable has to be in days. So when we talk about what's happening over 92 days, we're talking about what's happening from day 0 to day 92. If we were to integrate this function from 0 to 92, what would happen is we would find out the total change in temperature. So the original function here that we're referring to is temperature. We are given the derivative of the temperature function. And by looking at the area under this function, we can tell how much the original function changed or how much the temperature changed over this time period. So if we carefully enter all of this stuff into our calculator, we're going to get negative 41.78, and this will be in degrees Fahrenheit. So remember, the rate was degrees Fahrenheit per day, but then we were looking over days, so the days units cancel. So here we have something negative, and what that tells me is that the temperature function is decreasing by 41.78 degrees Fahrenheit. So the average temperature in January, on January 1st, is going to be 41.78 degrees lower than it was on October 1st. So the negative here is really important to tell us which direction the temperature is changing. So why does negative area make sense? It makes sense because in this circumstance, we need a way to talk about if our original function is declining, right? If it's decreasing. How do we talk about that? Well, since we're talking about the change in the original function, then a positive change would mean it was increasing, and a negative change would mean that it's decreasing. Now, this relates directly to what we know about derivatives. So if your rate is positive, right, like this, that tells you that your original function was increasing, which means that the area here is going to be positive, right? And so the amount of that area tells you exactly how much the original function is increasing. If, however, your function is below the x-axis, if your derivative is negative, that tells you that the original function was decreasing. And again, if we were to find that actual area, it would tell you exactly how much that function is decreasing. So that negative tells you the direction in which your original function is changing. So negative area is important because it tells us the directionality of the original function. But as a reminder, area is only negative because we are assigning a meaning to it to make it negative. Area by itself is always positive. So unless you're in a context where you're doing calculus and you're looking at the area of a known derivative function, then your area will be construed as positive unless you have a reason to make it negative. And so we're talking about here why we're doing that and why we're allowed to do that. And again, the reason we're allowed to do that is because the way we're measuring the area was with these rectangles, right, that were delta t times f of t sub 1, and this value, this f of t sub 1, could be negative if we were below the x-axis, which allows us to count that area as negative. Example 3. Given the graph of f of x below, determine which intervals will yield positive areas when calculated with the definite integral, and which intervals will yield negative areas. So giving it a cursory look, I see that the purple areas are above the x-axis and the beige areas are below the x-axis. So I know that the purple areas, because they're above, are going to be counted as positive. Again, because when I draw in my rectangles, even if I draw in 1,000,000 of them, the y values are going to be positive from the f of t sub 1 values. My beige areas are going to be counted as negative because, again, I'm looking at this area with the lens of the definite integral, which means that when I draw in my rectangles, the y values will be counted as negative. So here, my positive integrals are going to be the integral from roughly, let's say that looks like it's around 1 to 5 of f of x dx. And this looks like it's roughly 8 to 9. So 8 to 9 of f of x dx. Those are going to give me positive integrals. My negative areas are going to be the integral from 0 to 1 of f of x dx, and the integral from 5 to 8 of f of x dx. So again, area above, we're going to count as positive when talking about the definite integral, and the area below we count as negative when talking about the definite integral. So now we need to ask the question, what happens when we have both and we want to look at an entire interval? That'll be discussed in the next video.